So here we go. We just did our quiz, and so now we're looking over the videos for Chapter 7, Section 2, Properties of Rational Exponents. We already started some of this in 7.1. Now we're going to go into more depth of what we can do with these properties and where I can go. We're going to work on this for 3 days. We're going to talk about conjugates, and then we're going to have a quiz next Monday. So now you've heard it first. There's a quiz next Monday. So let's go ahead and remember our properties of rational exponents. So when I'm looking at rational exponents, when my bases are the same, I add my two exponents. Bases are the same, I add the two exponents. Whenever I take a base and I raise a power to a power, I multiply my two exponents. Whenever I have two bases to the same power, I can distribute into that parenthesis. But I have to remember, this is multiplication. Down here, we're going to talk about the same thing. We're going to talk about division. I cannot distribute into addition and subtraction. I can only do it into multiplication or division. So AB to the M is A to the M, B to the M. Anything to the 0 power is 1. Whenever I'm dividing, I subtract my exponents. Whenever I'm dividing, I can distribute into that parenthesis. So I can do that for multiplication and for division. So let's do some examples over this and see what type of problems that may crop up looking into this. Again, when I look at this, remember that M is my power, my exponent. Whenever I'm looking at this, A to the M and N is my root, my square root, my cube root, my fourth root. I need to remember those. I need to keep those separate and know what they're doing. I need to have course pack page 706 next to me so that if I'm not able to do, so I can try to do this in my head using that page. If not, I'm going to go ahead and use my calculator. So for me, here's course pack page 706. I have it easy to get to. So let's go ahead and try this. The first thing I'm doing is I'm doing power to, my bases are the same, 3. So I add my exponents. So this is 3 to the 1/3 plus 5/3. So this is 3 to the 6/3. Now, the nice thing about the way powers and roots work together is they can reduce the way a normal fraction would reduce. So instead of trying to do the cube root of 3 and the cube root of 3 to the 5th power, I can add those and get 3 to the 6/3. Well, 6 divided by 3 is 2, so this is 3 to the 2nd, or 9. And that's my final answer. I can go ahead and say all these are equal. My final answer is 9. Now, let's take a step to the side and think about this one more time. Over here, this was the cube root of 3, and I'm multiplying that by the cube root of 3 to the 5th power. And notice these two things are identical. This is to the 1st power. This is to the 5th power. So this would be the cube root of 3 to the 6th power. Well, 6th power cube root reduces, just like what we said. And so I can, again, I get the same answer to be 9. But using just my fractions makes it a lot easier. 1/3 plus 5/3 is 6/3. 3 to the 6/3 is 3 squared, which is 9. So yes, could I do it using roots and powers? Yeah. Are fractions easier in this case? Yes, they are. Here's another case that fractions are easier. I'm dividing here. My bases are the same, so I can think of this as 5 to the 1/2 power minus 1/3. Now here's a case that I really couldn't do any other way except for fractions. How in the world do I deal with the square root of 5 divided by the cube root of 5? There's nothing in roots that allows me to do that problem. But since I can go ahead and make this into fractions, I can say, well, in a fraction, I can get a common denominator. And I can say this is 5 to the, well, the common denominator for 3 and 2 is 6. So 1/2 is the same as 3/6. 1/3 is the same as 2/6. So 5 to the 1/2 minus 1/3 is 5 to the 3/6 minus 2/6. Oh, now all of this is in my exponent. So this is 5 to the 1/6. So I'm saying that this is the 6th root of 5. That's my answer. I need to write that better. The 1/6 need to be an exponent, not like it's right next to it. Be careful with that. But 5 to the 1/6 is my final answer, which is the 6th root of 5. But if I was trying to do this with roots, I can't do it. There's no way that roots allows me to do that. But since I'm using exponents and fractions in exponents, I can get a common root. I can get a common denominator, and I can solve it down. So it allows me to do problems I could not do otherwise. So let's do a couple of other examples. So pause for station idea. Sorry, I had to drink some coffee. So the power of using exponents, what are called rational exponents, which I some calls fractional exponents, allows me to do things I couldn't do otherwise. 8 to the third to the 1/9 power. That means I want to take 8 to the third power, and then I want to take the 9th root of that. Oh my gosh, what in the world am I talking about? Well, use what you know. 8 to the third, I can always write any whole number as a fraction, so 8 to the 3 over 1, and this is power to a power, so I multiply. So 8 to the 3 over 1 times 1 over 9. This, again, all of this is in my exponent. 3 times 1/9. Well, again, 3 times 1/9, I just multiply the numerators, multiply the denominators. 3 times 1 is 3. 1 times 9 is 9. Again, this is all in an exponent. So this is 8 to the 3/9. And since I'm using fractions, I can reduce that to the 1/3 power. 8 to the 1/3 power. Well, what's that? That's the same thing as the cube root of 8. So the 1/3 power, or the cube root of 8, asks what number times itself 3 times is 8. I can go to my handy dandy form, look under my cubes. Oh, 2 to the 3rd power is 8. So the cube root, or the 1/3 power of 8, or the cube root of 8, is 2. And that's my answer. Could I have done 8 times 8 times 8 and gotten 8 to the 3rd power is 512, and then taken the 9th root of 12? Well, I don't even have the 9th root on the sheet. I'd have to look in my calculator. The 9th root of 512, you're right, is 2, but I can do it all in my head by using fractional rational notation in my exponents, because the fractions allow me to reduce my exponents, and it doesn't actually change the math. That's the nice thing of using these rational exponents. Okay, well, what can I do now? Again, I can use this 27 to the 1/2 power. What times itself is 27? Well, if I look over here, my squares, I don't have a square root of 27. If I look over here, I want the 1/2 power of 1/3. What's the square root of 3? Again, 3 is not a perfect square. I can't do this problem. It seems, excuse me, one wrong place. It seems I can't do this problem. But the nice thing is that I can actually, in my exponents, let's see, I'll write this down here. when the exponent, that's exponent, are common, are the same thing, like in this example, they're both 1/2, I can reverse distribute. When I have the same exponent, I can reverse distribute. It's kind of like factoring. I can reverse distribute. What does this look like? Well, 1/2 is my exponent, 1/2 is my exponent, so I can put parentheses, and now I'm pulling out a 1/2 power. My numerator stays 27, my denominator stays 3, and I just reverse distribute it. And I can say that 27 to the 1/2 divided by 3 to the 1/2 is 27 divided by 3 to the 1/2, because at any time I can distribute this 1/2 to the 27, this 1/2 to the 3. This is identical, equal to this step up here. But look what I can do with this. 27 divided by 3, oh, that's 9. Well, and then I want the 1/2 power of 9. Well, remember, the 1/2 power of 9 is the square root of 9. What's the square root of 9? Oh, yeah, that's positive or negative 3. I can do this problem now where at first I couldn't do it. So I had to use the power of the rational exponents and factor out, reverse distribute that fraction out. Reverse distribute the exponent so I can do some reducing first, and then I can work on the exponent. All right, a couple more examples. So look at this. Again, my bases are different, but my exponents are the same. Again, I can't take the fourth root of 6. I can't take the fourth root of 36. Look under 4s. There's no 6 here. Excuse me, there's no 36 here. So I can't take the fourth root of it. But if I look at this, my bases are different, my exponents are the same, so I can use that property and I can reverse distribute this. And this again is 6 times 36, and my 1/4 power sits nicely on the outside, and 6 times 36 is 216 to the 1/4 power. I can then look at my chart again. Well, 216 isn't a perfect fourth either, so it looks like I still can't do anything with this. I can't simplify it any further, but that is a simplification at that point, and so I'm done. There is no fourth root of 216, so I would leave it as it's 216 to the 1/4 power, but I can try to reduce it as best as I can. Example 6, well, my powers are not the same. My bases are not the same, but I can take this exponent and I can distribute it into both of my terms here. And so I get 3 to the 2/3 times 6 power times 4 to the 1/3 times 6 power. 2/3 times 6, remember, I can always think of that as 6 over 1. So this is 3 to the 2 times 6 is 12/3 times 4. Again, I can think of this as 6 over 1. 1 times 6 is 6. 3 times 1 is 3. So 4 to the 6/3. I can reduce 12/3 and get 3 to the 4th. I can reduce 6/3 and get 4 squared. Well, look at my handy dandy chart on page 706. 3 to the 4th is 81. 4 squared I know is 16, so 81 times 16. If I multiply that out, I get 1,296. A problem that looks very foreign. I can't do anything with the exponents. I can't do anything with my numbers. It's weird to take a 2/3 power here or a fourth or a third power here, but since I can distribute that power in, I get two nice numbers that I can multiply and find my answer. So what's the gist? What's the point? On the last sheet of my notes is this. The first thing I want to do is I want to distribute a power first. Get rid of the parentheses. The example is this. I would want to distribute the p into the x, the p into the y. Deal with negative exponents, deal with same bases, and then I want to do same exponents. I want to reverse distribute. I can always check for items to simplify. Always, always, always simplify. Okay, guys, that's the last of my notes. We're sitting right at 16 minutes. See you in class.